We're in chapter 8.1. We're finishing up this chapter. Carlos, Peña, and Hilomar, please turn on your camera. I'm sorry, we finished that last chapter. Now we're going to work on this one. Thank you, Carlos. And thank you, Peña. Hilomar, you're up. Thank you. All right, we're going to talk about the weather now, temperatures and winds. We're going to talk about the different seasons, how the sun positions itself based off of each time of year, and why some parts it's hot and some parts it's cold, and then the wind, how the wind affects that as well as the seasons change. So let's start with 8.1. I'm gonna read a little bit and then I'll have you guys read. The weather making. Where does lightning come from? What causes the tornadoes to spin? How do clouds manufacture snow? Why do breezes blow? Why does the bright sun warm the earth less in winter than in summer? Questions such as these have puzzled men for centuries. But in recent years, meteorologists, or the scientists who study weather, have succeeded in unraveling some of the mysteries of the sky. In this chapter, we will study some of weather's various ingredients. In order for us to understand the workings of weather, we first need to realize that the sun is the basic cause of all weather. The seasons, the winds, the clouds, the lightning, even the rain, are all results of the sun's influence over the earth. A filter for solar rays. The atmosphere acts like a giant screen or filter around the earth. In order for the sun's rays to reach the earth, they must first pass through the filter. Actually, an average of only about 47 of the sun's radiation manages to get through the atmospheric barrier. The rest is either reflected back into space or absorbed by clouds, dust, carbon dioxide, or ozone. The atmosphere prevents many forms of harmful radiation from reaching the earth. All right, playing hot potato. Who's gonna read? Who's gonna read?
Me, mister.
Mister, I don't have the book here.
Okay, Carlos, you read.
I too,
Okay.
mister. I don't have the book. I just know. My mom tells me that I have classes too.
Okay, Carlos, go for it.
The stratosphere. Above the stratosphere is a layer of the atmosphere called the stratosphere. Because there is almost no water vapor in the stratosphere, clouds do not form in this region. Aircraft often fly through the lower portion of this layer in order to escape the turbulence of weather. The temperature in the upper parts of the stratosphere can reach 37 F as ultraviolet rays
Wait a
from
second.
the sun warm the earth.
Carlos, it's at playing hot potato on chapter 8.
What? I didn't hear you. Wait. Playing hot potato.
Yeah,
That one.
yeah,
Okay.
keep going.
Not only does the atmosphere act as to block out certain form of solar energy, but it also acts as a huge heat absorbent blanket to keep the earth warm. After solar rays pass through the atmospheric filter, they strike the ground. The ground absorbs the solar rays and they releases the energy in rays of a slightly different form back up into the atmosphere. These heat rays are unable to escape into space but are absorbed by the atmosphere, which in turn radiates them to the earth as if they were playing a huge game of hot potato. The ground has the atmosphere, pass the energy back and forth to each other. This function of the atmosphere in preventing the Earth heat from escaping to space is called the greenhouse effect. Without the greenhouse effect, the Earth temperature would plunge far below freezing every night as soon as the sun went down.
Read that next part.
Continue.
Yeah, keep going. Finish that chapter. Sorry, that paragraph.
Okay. Second-hand heat. The air that we live in receives most of its warmth second-hand from the ground. First, the sun hits the ground, and then the ground, like a giant heater, radiates its warmth into the earth above. Because most near the ground, this air is much warmer than the air found a few miles higher out.
All right, so it's colder up in the atmosphere because the air near the ground absorbs more heat. All right, Liz, Benya, read me the seasons. Benya. Unmute yourself, bud. There you go.
The seasons. The Earth takes about 365 days to complete one orbit revolution around the Sun. As the Earth makes the journey, it also rotates on its axis, an imaginary line running through the Earth from the North Pole to the South Pole, like a spinning top. The Earth's axis does not run straight up and down in relation to Sun, but instead still at a slight angle. This still in the Earth axis results in the different seasons of the Earth. The equator is an imaginary line circling the Earth midway between the North and South Poles. The half of the North and Earth surface north of the equator is called the Northern Hemisphere. The half to the south is called the Southern Hemisphere because of the Earth is the Northern Hemisphere is point more directly at the sun for parts of the year than is the Southern Hemisphere. During the phase in the Earth orbit around the Sun, the Northern Hemisphere has its summer and the Southern Hemisphere has its winter. But a few months later, after the Earth has traveled around the opposite of the Sun, the Northern Hemisphere faces the Sun more directly and is summer when the Northern Hemisphere has its winter.
Very good. All right. Let's have Gloria, will you read A Matter of Angles?
A matter of angles. The difference between summer and winter temperature in each hemisphere are caused by variation in the amount of solar radiation, which includes many other types of energy besides visible light, falling upon the Earth. During summer in the Northern Hemisphere, for example, solar energy strikes the air directly, producing warm temperature. But in the winter, when the northern hemisphere is not pointed directly at the sun, solar energy strikes at a slant, spreading and shining out over a wider area. The energy acts like the beam of a flashing light. If you point the flashing light straight ahead at a wall, you see a small bright circle of light. But if you point the flashlight so that the beam strikes the wall at a slant, the light spreads out to make a line. Dreamer always shape. When you walk outside on a sunny winter day, you have less solar warmth streaking your body than you would on a bright day in the summertime. That is one reason your body feels colder. Another reason is that the air surrounding you is cold because it is also receives less energy from the sun. In the winter, solar energy are traveling at a slant must penetrate a greater distance than the Earth's atmosphere before it reaches the surface. The longer journey gives the atmosphere more of an opportunity to absorb the sun's rays or reflect them back into outer space. The increased blockage of solar rays and the shorter days giving the sun less time to warm the earth are other reasons why the earth temperatures are colder in winter than in summer.
Very good. Okay, so if this is planet Earth right here, okay? Let's look at it. And this right here is, I'll use my coffee mug. This is the sun. Which part is closer to the sun, the top part or the bottom part? Which part's closer, top part or bottom part?
Bottom part.
The bottom part. So in the bottom part, it'll be summertime. In the top part, it'll be winter. Because this is going to hit directly, whereas this is going to hit it as a slant. All right? Now, if we flip it and we have it this way, which part's closer to the sun? Top part or bottom part?
Top part.
Top part. This part will be wintertime. Right now, we're about here in wintertime. Or summertime here because it's changing to be wintertime in the northern hemisphere, which is where we live. And so it's hit at a slant, and that's why it's colder. For example, look at my hand, all right? If I just shine the light directly, you can't really see it here, but the light directly like that, it's just, see how if it's direct like that, it's just in one spot? So all in this area is gonna be warm. But in the wintertime, it's gonna look like that. So it has to spread all the light with all the top part of the northern hemisphere, which is why it's colder, because it's not getting hit directly, it's at a slant, it's getting spread out. Have you ever played with a flashlight?
Yes.
Yeah, and have you ever shined it on the ground but at a slant where it covered most of the ground? It's the same thing with the sun and the heat, okay? Let's keep reading. Monse, you're awake? You're asleep. Monse. Monse, wakey, wakey. Monse, I want you to read right now, the winds. I want you to read the winds.
What?
Page 205, the wind.
Mister, I cannot hear.
I want you to read, girl. 205, the winds.
What?
The wind 205.
Yeah.
What? Mister, wait, that my sister is. Mister, I cannot hear nothing.
The wind, page 205.
Thank you, Tara.
Italian. Mr. What is listening?
Like the seasons, their winds are also created by the sun. Winds are produced by the temperature differences found on the Earth. The greatest of these temperature difference exists between the equator and the poles. Tropical regions near the equator are not really affected by the tilt of the Earth's axis. No matter what the season, energy for the sun always strikes there directly, making the temperatures constantly warm. But the North and South poles are just the opposite. Even in the summer, solar radiation reaches them at a slant, and temperatures are cold. In the winter, they receive very little solar radiation, and temperatures plunge to the below zero. At any given time, the temperature differences between the tropic and the poles are very great, as much as 108 I don't know. Without winds, the equator would be much hotter and the poles would be much colder than they are now. Could God design winds to carry excess heat away from the tropical region and toward the poles? According to the wide plan of the Creator, this transfer of heat not only balances out the uneven distribution on the sun's warmth on the earth, but it also produces the cold and system of weather that water the earth. But how exactly do the wind transport heat from the equator to the poles?
Keep going, Monse.
Nothing but a lung of hot air. You have already learned that gases in the air expand when they are heated and contract when they are cooled. If air heated, the molecules in the air spread out over a greater area, meaning that any particular area of space will hold fewer air molecules than it did before the air was heated. Cold air is denser than warm air and holds a great number of molecules in the same amount of space. Since warm air is made up of more empty space and fewer molecules of matter, it weighs less than cool air. Cool air is heavy and has a tendency to fall and settle near the ground. Warm air rises when heavier. Cool air gets underneath it and pushes outward. A good example of recent power of a warm air is seen in a hot air balloon. Air inside the balloon is inside and expands rapidly.
Finish the paragraph.
It is it is so much lighter than the unheated air around it that it is able to raise not just itself but the balloon and the gondola, the place where people ride as well.
All right. So with the wind, it carries away the heat that is not needed, so it moves it around. So it's not just really, really hot in one area. It gets spread out, which is really nice. And with heat, warms up air, so it makes it rise, whereas cold air makes it fall. For example, if you're in a building that's on fire, they say to drop to the ground because all the smoke and the heat's gonna rise up and you'll be on the ground where it's not gonna be there. So that's why they say drop to the ground, because the heat of the air rises. And now let's see. Lizzie, you don't have your book?
No, Easter.
And half of the class doesn't have their book. You guys need to have your books. All right, I'm gonna read.
What, Mister?
Half of the class doesn't have their books. You guys need to bring your books when you have class. All right. I'm gonna read from
It's
here.
because my mom just told me that we are a class as two.
Okay, easing the pressure. You will remember that air pressure is the weight of the atmosphere pushing down on the earth. When warm air rises, it counteracts the downward push of the air's weight by moving in the opposite direction. Air that is moving up does not press down on the Earth's surface as hard as stationary air does. Rising air then actually reduces air pressure at ground level. In the same manner that an umbrella shields you from the rain or sun, rising air shields the area below it from the full weight of the atmosphere. When cool air settles near the ground, it has the opposite effect on air pressure. Air pressure at ground level is increased, not decreased. The downward motion of the falling air strengthens the normal downward push of the atmosphere weight and adds to the total force pressing down. Sorry, I lost my place. The downward motion of falling air strengthens the normal downward push of the atmosphere's weight and adds to the total force pressing against the earth. When placed under high pressure, air always seeks to flow to an area of lower pressure. For example, air under pressure in a balloon will always rush out of the balloon unless the end is tied. In the atmosphere, air in a region of high pressure behaves like air escaping from a balloon. Air always flows away from the region of high pressure to fill the region of low pressure. So it'll move out like that. Okay, so push down and then go out. And so when it's colder, there's more atmospheric pressure at ground level than when it's hotter because hot air is pushing up against it. All right, let's go to 208. Carlos, I want you to read again.
What, mister?
I want you to read again.
Wait.
208.
Earth-sized winds. In the tropics of bright sun makes the earth, land, and ocean surface unusually warm. The earth in turn heats the air above it. Warm air over the tropics rises because it is pushed up by cooler, heavier air surrounding it to the north and the south. The rising warmth creates low pressure below it at ground level. Cool air are both the north and the south flow across the ground toward the equator to fill in the low pressure area. On the earth is flowing air is felt as wine. At the same time that air near the ground flows toward the equator, air at upper level moves like the opposite direction. As the heated tropical air rises away from the warm earth, it cools with the increase in altitude, height, until it is not light enough to move upward any further. Then it began to flow away from the equator. As it moves away from the equator, it cools even more and falls slowly downward to the earth to replace the earth moving at ground level toward the equator. The circulation is continual, with warm air rising at the equator. Cooling air flowing outward, settling to the ground far to the north or south, and flowing back to the equator to be warmed over again.
All right, very good. So that's what the air does. So it makes it just a giant circle. So it'll move to the equator, be warmed up, and then go up, and then get cooled, and then go down, and then move to the equator, be warmed up. And so it just does a giant circle like that over and over again. Gloria, will you read a spin that makes the atmosphere dizzy?
A spin that makes the atmosphere dizzy. The Earth is a big place. It is so big in comparison to use that we never notice its motion. In the 365 days that make up 1 year, that Earth travels about 584 miles, moving at 66 miles per hour. That means that if you are 10 years old, you have journeyed almost 6 billion miles in your lifetime. You probably had no idea that you were that kind of a cosmic traveler. And at the same time as it is spending such space in a track around the sun, the Earth also turns on its axis, completing one rotation in 24 hours. Of course, you know that the Earth rotation causes sunrise and sunset every day, but you may not have known that in order for the Earth to keep up with its schedule of 24-hour days, the Earth's surface has to spin around at over 100 miles per hour. To us, the Earth appears to rotate ever slow, and the sun and moon seem to creep across the sky. If the Earth did not rotate, the Earth winds will be every predictable. Warm air will rise at the equator and flow all the way to the north and south poles, where it will cool and settle. Then, attracted by low pressure, it will flow along the ground back to the equator, warm up, and rise to begin the cycle again. To people on the Earth's surface, the winds will always appear to come from the north in the northern hemisphere and from the south in the southern hemisphere.
Very good. Peña, you're up. The three major wind systems. Very good.
The Earth's rotation makes the transfer of heat from the equator to the poles much more complicated. Winds here at the equator is not able to flow due north to south to the poles. It can only about a third of the distance before it falls back toward of the Earth and gets caught in return fall to the equator. The flow of air is not due north absorb either the Earth's rotation bends the winds of the northern hemisphere that blow from the northeast and the south hemisphere. From the southeast, these winds in this part of the world are called the trade winds. Therefore, I continue, Mr.
Finish the page.
Therefore, away from the poles is similar to the flow of the equator. Cold ground near the poles travels only about the entire of the distance of the equator before reaching and returning of the poles. Bent by the Earth's rotation, the winds in this are called the polar sterlies. The polar sterlies, like a region where the tropical and the polar airflows meet in these middle latitudes, the winds affected both by the Earth's rotation and by the pressure difference between the airflows blow out of the west. The arrows in both hemispheres are referred to as deviations of purely westerly collisions between warm tropical air and cold polar air give the middle latitudes the most chill weather on the earth.
All right, very good. So let's talking about the different types of wind systems. We have the trade winds, which push towards the equator, and then the polar easterlies, which are pushing down, and the prevailing westerlies, which are pushing up. All right, or towards the poles. They're pushing towards the poles. Let's see. So 8.1, you guys have to do 8.1. Let's go to 8.2 real fast.
Mister,
Yeah,
can I go to the bathroom?
we're about to be done. Can you wait a little bit?
Okay.
Okay, perfect. All right, now we're in 8.2. I'm gonna start reading a little bit. When you think about weather, this is about water vapor. When you think about weather, you do not usually consider the rotation of the earth or the winds that circulate over the tropics. You are more interested in today's forecast for your area. Is it gonna rain today? Is it not gonna rain today? Will it rain or snow? Is there gonna be sunshine today? Or will the sky be cloudy? Will it be cold enough to wear a jacket? You want to know the forecast because local weather conditions can greatly affect many of your day-to-day activities. For example, a little bit of rain might determine whether or not you'll be able to play outside after school. In the last section, we talked about the different seasons, temperatures, and winds that are found across the Earth's surface. These things make up weather's big picture. Now we're going to zoom in to take a closer look at various types of weather as you could observe them from the ground in your own hometown. The smaller building block of weather includes such things as clouds, rain, snow, and storms. They depend upon another essential ingredient of weather, water vapor. But before we can go on to learn about clouds and storms, we need to talk about how water vapor behaves when it is mixed with the air. So water vapor is basically small particles of water that we don't really see, but they're there. Humidity is relative. The air we breathe contains a small amount of water vapor. Depending on the temperature of the air, there is a limit to how much water vapor the air can hold. Warm air can hold much more water vapor than cold air can. We refer to the amount of water vapor in the air as the humidity of the air. Humidity is measured by a percentage. The humidity is 75, for instance. That means that the air contains 75% of the water vapor it is able to hold at that temperature. The humidity is at 100%. We say that the air is saturated. Saturated air at a particular temperature contains the greatest amount of water vapor air can hold at that time. A humidity measurement tells us how full of water vapor the air is. Because warm and cold air are able to hold different amounts of water vapor, the humidity percentage is a relative measurement. That it is relative to or based upon the temperature of the air. We refer to the measurement of humidity as the relative humidity. It takes water vapor to produce a humidity reading of 100% at a high temperature than it does to produce the same reading at a lower temperature. For instance, saturated air at a temperature of 90 degrees Fahrenheit contains the same amount of saturated air at a temperature of 30 degrees Fahrenheit. But both quantities of air have a relative humidity reading of 100% because they both hold as much water vapor as it possibly can at the different temperatures. All right, for example, here's my water bottle. It's about halfway full. And if I poured all that water into this cup, it would fill that cup up. And so this is 50%, but this is 100%. That's because it's at different sizes. So if it's colder, it's because it's at 100%, which means that it can't hold as much water as hot air can. You know what I mean? And so if it's cold, if it says, it's just like using 2 cups of water like I showed you. One of them, the smaller one, would be a colder temperature. So even though that's full, but they have the same amount of humidity, it's because colder can't hold as much water vapor as hot air can. And so it's just the temperatures. Colder temperatures hold less water vapor, and so they'd be full more. The air would be full more water vapor, whereas in hotter temperature, can hold more. We're going to talk about dew points real fast, and then we'll be done. The dew point. As air cools, it loses some of its ability to hold water vapor. Let's imagine we have a room full of very warm water at 45% relative humidity. If we cool the room down a few degrees, the relative humidity will rise, say, to around 60%. The amount of moisture in the air has not changed, but the total amount of water vapor the air can hold has been decreased. So it all depends on the temperature. So if it's at 45% humidity and it cools down, it'll move to 60, which means that it's cooling down. So it's like almost the cup is shrinking. And so water is going to start to escape. If we continue to lower the temperature of the air in the room, the relative humidity of the air keeps on rising. Eventually, the relative humidity reaches 100%, and the air becomes saturated. The temperature at which cooling air becomes saturated is called the dew point. So it's like you're filling a cup with water. It's eventually going to pour out, and that's what the dew point is. When it gets cooled down to a point, that's when it finally is starting to show. For example, when you guys played soccer at the school, maybe you were sweating a little bit, but once you got inside the room and it was full of air conditioning, did you sweat a lot more? That's because the temperature was cooler, so all the water vapor was starting to be shown, okay? The temperature at which cooling air becomes saturated is called the dew point. The dew point is not one fixed temperature, rather it varies depending on how much water vapor the cooling air contains. Air that contains a large amount of water vapor will have a higher dew point temperature than air that contains a very small amount of moisture. The air in the room started out with a relative humidity of 45%. Its dew temperature is higher than it would have been if it had begun with a lower relative humidity of 30%. All right. Now, let's read condensation and then we're done. The dew point is the lowest possible temperature at which air is able to hold all of its water vapor. If saturated air continues to cool below its dew point, it must release some of the vapor. Released water vapor leaves the air and changes back into liquid water in a process called condensation. We see the results of condensation around us all the time. Have you ever sipped a tall glass of lemonade on a hot day? If so, you have probably noticed that the outside of the glass becomes very wet. For example, look at my cup. See how it's wet at the bottom? That's condensation. Know that the moisture is not lemonade oozing out of a crack in your glass. It is pure water released through condensation. When the hot, humid air surrounding the glass was suddenly chilled by coming into contact with the cold glass. The hot air, cooled below its dew point, deposited its excess water vapor as a liquid onto your glass. Riding in the car with your family on a cold night, you may wonder why the windows are all fogged up. Again, the cause is condensation. The breath of the people in the car makes the air inside much more warm and moist than the air outside the car. When the humid inside air is cooled below its dew point, through contact with the cold glass, the result is a thin, misty layer of water on the inside of the windows. During the day, the Earth's surface absorbs heat from the sun. Then at night, the Earth radiates this heat back into the atmosphere. As the ground gives off heat, it cools faster than the air above it, and the temperature of the ground drops quite a bit lower than the temperature of the air. The warmer air just above the ground is cooled by contact with the cold ground. What do you suppose happens when this air is cooled below its dew point? You can easily guess. Dew forms on the ground as the water vapor in the air condenses. The temperature of the ground is below freezing. The water vapor freezes, forming frost on the ground instead of dew. Okay, that was long. We're finally done. Let me explain what you guys have to do, all right? So, in comprehension check 8.2, define what dew point is, condensation, dew, and frost. And then you have to write on the essential weather ingredients. Essential weather ingredients to things like clouds, rain, and storms depend what is needed. We just talked about it. And then which is able to hold more water vapor, warm air or cold air. And then as air cools, what happens to its relative humidity? And we have, what do we call air that has reached 100% humidity?
This and 8.1, we need to do it.
Yes, as well. And then can you explain why the bathroom mirror is fogged up after you take a shower? All right, and then you have to do that is what you guys have to do. Sound good?
Peter,
Yes.
Already
Yeah, mister.
Phase one. Look,